Today we're going to talk about congruent triangles. First, we need to remind ourselves what the word congruent means. So far, we've learned that to be congruent means to have the same measure. We have also learned the symbol for congruence. It is an equal sign with a swoop on top. Congruent figures, then, are figures that have the same shape and size. All of their corresponding pieces have the same measure. Now, when I say the corresponding pieces, I'm saying that the base of the triangle needs to be congruent to the base of a second triangle, and then the one side needs to be congruent to the other side, and then the third side needs to be congruent to the third side. In addition, their corresponding angles have to share the same measure. We have a theorem in geometry known as CPCTC, which is sort of a mouthful, but it stands for the fact that corresponding parts of congruent triangles are congruent. It's verifying what we were saying by definition. It means all the matching sides and the matching angles have the same measure. We have what is known as a congruence statement. This right here reads triangle ABC is congruent to triangle DEF, and this is our congruence statement. The congruence statement serves the purpose of telling us exactly which pieces are corresponding. For example, the first letter represents the first set of angles that are congruent. In our diagram, angle A will be congruent to angle D. Those are the two that correspond according to our congruent statement. Angle B goes with angle E. Notice I'm using a second set of tick marks so that we don't feel like A and B are congruent, but we can clearly see that A is congruent to D, B is congruent to E. And finally, you might have guessed already, that C needs to be congruent to F. The congruent statement also tells us what sides are congruent. I can see that side AB, the first two letters in the left-hand side, would be congruent to the first two letters on the right-hand side of our congruent statement. So AB is congruent to DE. BC is congruent to EF. And AC is congruent to DF. It is very, very important that you rely on the congruent statement to tell you what pieces are congruent and not the diagram. If you looked at the diagram, you may have assumed that A was going to be congruent to F based on the orientation of the two triangles, and that would be incorrect. You would miss out on measurements or working the math for finding the missing parts if you were putting together the wrong angles or the wrong sides. So the congruent statement is the important key to knowing which pieces correspond and therefore which pieces are congruent. We are going to be talking about how we prove two triangles congruent. Right now, what we have is a definition that says that all corresponding angles and sides need to be congruent in order for the figure to be congruent. Using our congruent statement, I have come up with this list of angles and sides that needs to be shown to be congruent. I just used my congruent statement to see which ones corresponded, and if I were going to write a proof, this would be a lot of things I would need to show, and it would make for a very long and tedious proof. So we're fortunate that we have several shortcuts. We can reduce the amount of work that's required in order to declare two triangles congruent. We have four postulates for regular triangles. The first one is called the side-side-side postulate. We abbreviate the side-side-side postulate with the initials SSS. And the postulate says if three sides of one triangle are congruent to three sides of another, then we can declare the two triangles congruent. So if we can come up with a way to mark two triangles in this fashion, where the first side's congruent to the first side, a second side congruent to a second side, and a third side congruent to a third side, notice we don't have to say a thing about the angles. The sides are enough. Three sides to three sides, those two triangles are congruent. We are going to be asked to list a postulate that we could use to prove two triangles congruent. This process is a matter of looking at what is given in the figure and what else we can add to the figure to decide which postulate we could use to declare them congruent. When I look at this picture, I can see the first triangle and the second triangle, and I ask myself what is already given. Well, I can see that one side's congruent to one side, a second side's congruent to a second side, and this side in the middle happens to be in both triangles. It should be congruent to itself. Therefore, I have three sides of one triangle congruent to three sides of another triangle. That means I could use the side, side, side postulate to declare those two triangles congruent. The next postulate we're going to talk about is the side angle side postulate, and you can probably guess that we're going to abbreviate that SAS. This postulate states that if two sides and the included angle of one triangle are congruent to two sides and the included angle of another triangle, we can declare the two triangles congruent. What do we mean by the included angle? Well, let's start off with saying that BC is congruent to FD, side 1 to side 1. AC to DE, that would be side 2 to side 2. So we have two sides of one to two sides of the other. Now we need the included angle. Well, the included angle is the angle that's formed where the two sides come together. So that would be this angle right in here. If I could say that the two angles that are included between the two sides are congruent, I could declare these two triangles congruent. So let's take a look at this set of triangles. Right now we have two postulates that we could use, the side, 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 and the side angle side postulates to declare these two triangles congruent. Right now I see one side to one side, a second side to a second side. So I either need a third side or I need an included angle. Well, I cannot go around declaring sides congruent just because I want to. So when I look at this, there is nothing that gives me any indication that I could get the third side to the third side. I also can't just go around declaring angles congruent. I have to have a justification for it. And in this case, I do. Take a look right here. What letter do you see? We see the letter X, then we know that we have vertical angles. And what is true about vertical angles? Vertical angles are always congruent. So I know that that angle on that side has to be congruent to that angle on that side. And look what happens if I mark what I have. I have a side to a side to a side, and an angle to an angle. Therefore, I'm choosing side angle side to declare these two triangles congruent. I may need to also write a congruent statement telling which sides corresponded to which sides. So in this case, let's start with the left-hand side triangle. If I start with the W, triangle WHE needs to be congruent to triangle what? Well, we have to match up the pieces that were congruent. Notice that this side, WH, is congruent to WL. So WH needs to be congruent to WL, and then I went from W to H to E. I need to go from W to L to O. And let's look. Is angle W congruent to itself? Yeah, they're in the same spot. And is WE congruent to its partner WO? Sure. So I have my triangle congruent statement written in the correct order. The next postulate is the angle-side-angle postulate. This postulate states if two angles and the included side of one triangle are congruent to two angles and the included side of another triangle, then the triangles are congruent. Basically, we've just switched the order between angles and sides if we compare this to the side-angle-side postulate. So we need two angles. Let's say that angle A is congruent to angle H, and angle C is congruent to angle J. Those are our two angles. Then we need the included side. Once again, the included side refers to the side that comes between the two angles that we are using. So our included side would be AC and HJ. If we were writing, we would show that we had an angle to an angle to an angle, and a side to a side. We can see the pattern that's set up makes us choose angle, side, angle for our postulate. So right now we have three postulates that we could use. We could use the side, side, side postulate, side, angle, side postulate, or the angle, side, angle postulate. Those are the ones we've learned so far. When I take a look at this figure, triangle 1, triangle 2, forming a rectangle, I notice I have no congruence marks. Instead, I have parallel lines. Well, if I have parallel lines are going to lead to angles that are congruent. So you might look here and see that there's the letter Z, which means I have alternate interior angles congruent when I have those parallel lines. In addition, I have parallel lines going this way. So I have a second letter Z here that you can see. And that allows me to say this angle here is congruent to this angle here. You might need to turn your paper sideways to see that Z, but those two parallel lines give me those two congruent angles. So right now I have this angle to this angle, and I have this angle to this angle. It sure would be nice to have the side that was included. And here's where a funny thing happens. If we have this side here, I'm highlighting it in blue right now, it is the same side in both triangles. ER is the side in the first triangle, ER is the side in the second triangle. Well, any side should be congruent to itself. We have a funny property that is known as the reflexive property. And the reflexive property states that a side or an angle should be congruent to itself. So we can declare that that side is congruent to itself by the reflexive property, and therefore we now have angle, side, angle as our choice for which postulate we would use to prove these triangles congruent. The last postulate of this type that we're going to talk about is the AAS postulate. I imagine that you can probably figure out that AAS stands for angle, angle, side. Now when we look at the name angle, angle, side, notice this time the side is not between the two angles. So this postulate says if two angles and the non-included side of one triangle are congruent to two angles and the non-included side of another triangle, the triangles are congruent. So let's mark angle A, angle H congruent, and angle C and angle J. The question is, which one is the non-included side? A minute ago, we said that this would be the included side. And we don't want the included side this time, we want the non-included side. So we have two choices for non-included sides. It could be BA congruent to HI, in which case we'd have angle, angle, and the side that's not included, to angle, angle, and the side that's not included. Or we could have chosen this side to this side. Either one of those sides are not included, and therefore they set up the angle, angle, side not included postulate. We now have a total of 4 postulates that we could use to prove these triangles congruent. When I look, right now, I have a side to a side and an angle to an angle. So I need to look and see, are there any other sides or any other angles that I also know to be congruent? And this takes us back to our X shape. I see that X shape, which means I have what kind of angles? I have vertical angles. And vertical angles are always congruent. So that gives me another angle to another angle. So I have angle, angle, but the side this time is not included. The side is not between the 2 angles. So I have to go with angle, angle, side not included. It's very important when you go to study this material that you are paying attention to what are the postulates in addition to what are not postulates. So right now we have side, 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 angle, side, angle, side, angle, and angle, angle, side. Those 4 are postulates. Notice we have not said that angle, angle, angle is a postulate, nor have we said side, side, angle is a postulate. These 2 do not work. When we have all 3 angles of a triangle, for example, we can have a triangle that is 30, 60, 90, and have another one that is also 30, 60, 90, and yet they are completely different sizes, so they would not be considered congruent. So these 2 are not postulates. It's very important that you know they're not, so that when you're in the middle of working the problems, you're not just accidentally throwing together any letters that look like they would work. We have one last special case postulate. This postulate only works for right triangles. It's known as the HL theorem, and the H and the L stand for hypotenuse leg. The theorem says if the hypotenuse and a leg of one right triangle are congruent to the hypotenuse and the leg of another right triangle, then the triangles are congruent. So we need 3 things. We need a right triangle. Both of our triangles have to be right triangles. Then we need to know that the hypotenuses are congruent in both triangles. Hypotenuse, remember, is always across from the right angle. And then we need one of the legs congruent to one of the legs of the other triangle. If all those 3 things exist, we could say the 2 triangles were congruent. So if you're keeping count, we now have 6 ways to prove triangles congruent. The first one is the definition of congruent figures. That requires that we show all legs and all angles congruent before we can declare the triangles congruent. It would be tedious and long to use the definition. So we have come up with 4 postulates that are useful: side, 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 angle, side, angle, and angle, angle, side. And then we have one final postulate, HL, that's useful for right triangles only. So 6 ways, 4 of them for use in proof writing for regular triangles, 1 for use with right triangles, and a definition that tells us what congruent figures are to start with.